In this lesson, we're going to continue to examine some discrete probability distributions, but we're going to look specifically at ones that are uniform. A uniform distribution means that we are going to do one trial of something, and each outcome should be equally likely. In other words, something like flipping a coin. If I flip a coin once, there's an equal chance I can get heads or tails, 50-50. If I were to roll a dice once, there's an equal chance I get a 1, a 2, a 3, 4, 5, or 6. They're all 1/6. Okay, if I pull a deck of cards and take one card out of it, every card is equally likely. Okay, so let's look at an example here. A calculator has been programmed to generate a random number between 1 and 5. Why is this uniform? Well, each outcome is equally likely. That's the whole idea of uniform. Okay. Part B, I want to make my probability distribution. Remember, a distribution from yesterday means we're making ourselves a table. So X stands for the different things I could get, my values. So I could get any number between 1 and 5. So 1, 2, 3, 4, 5. What's the likelihood of these? Well, the first one's 1 out of 5. The next one's 1 out of 5. And 1 out of 5, 1 out of 5, 1 out of 5. This is the whole idea of a uniform, that each one is just as likely as the others. And if I want to sketch a graph of this, I can do that. Probability graphs look like the values across the bottom and the likelihoods across up the axis. So what could I get? A 1, a 2, a 3, 4, a 5. What's the likelihood of each of these? Well, they're all 1/5. So I'm going to have 5 separate dots that are all the same height. They're all equal, uniform, the same. Okay, calculate the expected value. Okay, so we learned about that little formula yesterday. Expected value is my value times my probability plus my value times my probability. Oops, wrong spot there. And so on, right? As many times as we need to do it. So how's that going to work for us? Well, the first value is 1. It's 1/5. The second value is a 2, 1/5, 3, 1/5, 4, 1/5, so on. We said there's a little shortcut from yesterday. If they're equally likely, I can common factor out the 1/5 and multiply that by the sum of each of the things I can get. Which in this case, probably not a whole lot faster having to write it out, but it does work. So 1/5 times 15. I should expect to get 3. Does that mean my calculator is going to come up with a 3? No, this is a theoretical value. This is what happens on average. Okay, so let's try a new one. This is a whole bunch of examples. They just get really good with using uniform distributions. A spinner, equally spaced and numbered 1 to 6. The fact that it's equally spaced means that they're equally likely to hit. In a particular game, a player wins points equal to triple the sector's value if it is a prime number. For all other spins, the player loses double the face value of the spin. Is this a fair game? So, we learned yesterday about fair games. Fair games are ones that have expected values of 0. So the question is asking us to find the expected value without ever actually saying that. How can we do this? Well, let's take a look. We kind of need to know what we spin. And based on that, what is its value? And based on that, what's the probability? So what could we spin? A 1, a 2, a 3, a 4, a 5, or a 6. Now they're all equally likely. They're all 1/6. But they don't have equal value. The value depends on the kind of spin. And we said if things are prime numbers, you get triple the value. So it makes me think about what is a prime number. Prime numbers are numbers divisible by 1 and itself, starting at the number 2. 2 is the smallest prime number. So if I spin a 2, I actually get 6 points, triple it. If I spin a 3, also a prime number, I'll get 9 points. If I spin a 4, it's not prime. So what happens for things that are not prime? We lose double. So for a 4, I'm going to lose 8. I'll go back and do the 1 also, not prime. 5. 5 is a prime number. It's triple. 6 is not. So, is this fair? Well, let's find our expected value. There's 1 6 each time times -2 plus 6 plus 9 minus 8 plus 15 minus 18. And my objective is, for fair games, to get expected value of 0, which means the stuff in the bracket hopefully comes out to 0. And if I add that up, I get 15, 30, 30 minus 28 gives me 2. Ooh, that is not 0. So this is not a fair game. And let's look at part B. What if the game were changed to points were won with even values and lost according to the odd values? So let's get rid of the prime idea. Maybe that's causing this to not be fair. And let's just go with evens and odds. So for part B, I still have the same outcomes, same probabilities. Those won't change. 1 6 all the way down. 1 2 3 4 5 6. But this time, if I spin an odd number, I'm going to lose points. And if I spin even numbers, I'm going to gain points. 1 is odd, so I lose a point. Gain 2, lose 3. Gain 4, lose 5. Gain 6. Let's find our expected value this time. -1 plus 2 minus 3 plus 4 minus 5 plus 6. What's that going to come out to? Okay, if I add up the positives, 2, 4, and 6 makes 12. The negatives, I get -9. So 12 minus 9 is 3. I end up with a half. Is it fair? No, still not fair. In fact, if we go back, the other one was 1 6, or sorry, 2 6, which is a third. This is a half. It's actually gotten less fair if you think about it. Okay, someone still has an advantage. The advantage happens with whoever goes first, right? Like you're thinking you're going to get to move forward. You're going to get to win something every time. You have a positive expected value. Okay. Well, let's work it backwards. Maybe we're the game designers and we want to figure out how to make it fair. So I have a 12-sided die. We're going to allow players to move forward at triple the face value if an even face is showing. I want to make this game fair. So I want to figure out what should happen to odd things. So let's think about this. My face, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Lots of different faces. And I know my value for getting something that is even, I get triple. So I know I get 6, I can get 12, I'm going to get 18, I'm going to get 24, I get 30, and get 36. But I want to make it fair. My expected value has to come out to 0. So in other words, all this forward movement has to be counterbalanced by backward movement for odd numbers. So how am I going to figure that out? I need to have some sort of thing happen that when I multiply my face value times what happens, it counterbalances. I don't know what that value is. How about I call it, I don't know, X. X is my odd thing. So what has to happen here? I know that my expected value has to come out to 0. It's going to be made up of 1 times something. 1 times something. Plus, I get 6 for getting 2. And 3 times something. And then I get 12. And 5 times something. And then I get 18. And 6 times something. 7 times something. And so on, right? I know this has to happen. But if I want them to counterbalance, not only do I have to 7 times something, I need that something to actually come out to a negative value, right? I need this to come out to something that makes it come out to 0 in the end. That's my whole big thing here. So I need these numbers to actually come out to minuses. And then we have the rest of them here. We had 24. And then we're going to lose some numbers for 9s. And then we had 30. Then we're going to lose some numbers for 36. Or sorry, for 11. And then we get 36. Okay. I need this to counterbalance itself. Now, it looks complicated, but it really isn't. If I add these up, add up all the green numbers, the positive movement, 6 and 12, 18 plus, oops, plus sign right there, 36, 60, 90, 126 ways of moving forward, has to be balanced out with the 1, the 3, the 5, the 7, so what's that, 4, 9, 18, 25, 36, moving backwards. And this is something I can solve. 126 on this side, 36x on this side. If I divide 126 by 36, hopefully you guys got x being 3.5. Okay. What does that mean? For every odd number should lose because negative, 3.5 spaces. Now notice I didn't even talk about the probability part because everything's equally likely. The probability part doesn't actually come into play here because I just need my positives, my negatives, my forward, my backwards to balance each other out to make something fair. Okay, let's try one more. And I just want to really work with these uniform ones because as soon as we start adding other ones in, it gets kind of confusing and it's hard to keep track of which one we're doing. So let's take a look at this last one here. A lottery. Ticket costs $5. A total of 2,225,000 tickets are sold. The prizes and their frequencies are shown in the table below. Find the expected winnings. How much should you expect by just buying a ticket? We can find that. What do we need to know? We need to know our probability. What's the probability of winning first prize? Well, there's 1 out of 2,225,000 tickets. How about second prize? Well, it's 2 out of 2,205,000 tickets. And third prize, it's 5 out of. And so on, right? 20 out of and 100 out of. Same number. In other words, kind of like uniform. How much should I expect to win on a ticket? Well, to win first prize, the value of it, it's worth 600,000, and the likelihood of winning it is 1 out of 2,225,000 tickets. How about second prize? Well, second prize is 60,000, and again, oh, I got 2 out of 225,000. And third prize, 6,000 of them, or $6,000 value, and there's 5 of them. And fourth and fifth. Now, this is a lot of fractions to put in my calculator. So, how can I use that cheating idea, the idea of a common denominator that I can take out to make my life a bit easier? Well, I hope you notice that they all have 1 out of 225,000. They all have that number in it, right? And don't forget there are more over here. I just didn't write them out. Times the values. That's what we've always done, right? The values of things. Now, the first prize obviously is $600,000 here. The value of second prize is 60, but there are 2 of them. So if I take these and multiply them together, I actually have a second prize of $120,000 to give out. Not one person's getting it, but I'm giving that out. Third prize, 6,000, and there's 5 of them. So there's $30,000 to give out for third prize. Fourth prize, 600 times 20, $12,000 to give out. And last prize, 60 times 100, there's $6,000 to give out. Now again, I'm not giving this to one person, but that's how much money I have to give out. It's the total value. So really, I can use that shortcut idea, which is the whole idea today. If I think about the value of stuff that I'm actually giving out. Okay, so if we add those up, what, 720, 750, 762, 768, I think. Okay, and if you do that, you should get, I think it's 33 cents. Okay. Your expected value, just for buying a ticket, you should expect to win 33 cents. Can you win 33 cents? Of course not. But this is our theoretical amount that we're giving out for every ticket. I do that by taking my total value, how much stuff I'm giving out altogether, and dividing by how many tickets there happen to be. Okay, that's the end of those ones. We're just going to try a couple. I want to make sure we can understand uniform things, expected value, before we move on to the more complicated ones tomorrow, which is a big, giant formula we're going to have to learn in a different situation.